Thank you very much for inviting me. This is a tough session after lunch, last session. I'll do my best. And it's not about tools verification. So everything's wrong. We could have been in the AI session and the other way. And also, thank you very much for the invitation, but we have not yet done space. So I hope to be able to come out of here working with some person in the room and be able to take our technology to space, which we've never done it. But we do have a lot of things to say on the RISC-V space, and we have a lot of good technology on RISC-V space, and I'll be talking about that technology. A little bit for the few of you that have never heard of us, we're 100% European, currently 130 employees. Everybody's in Barcelona except our sales team, which is in Munich, Volker's here, Seoul, Shenzhen, and California. What do? We license RISC-V IP for AI, right? So we sell an out-of-order CPU, RISC-V, of course, out-of-order vector unit, and out-of-order tensor unit. So everything works out of order, everything is connected, it's all in one, right? And we combine it, and this combination actually took us a lot of effort, and we're really proud of it. So we call it all-in-one because it's very different from what other people do, right? And this is the picture you're seeing. It's not a floor plan, it's a cartoon, but I love it because it looks like a floor plan. It's the RISC-V CPU in control, vector unit, tensor unit, and something we'll talk a little bit about the gazillion unit, right? So why did we do this work, right? If you are building an SoC or you're thinking about some of you sending an SoC into space, it's quite likely your SoC looks a little bit like this. This is what we call the old style SoC. You're going to have some CPUs, hopefully not ARM, but good, who knows. And then you'll have to buy a GPU from someone. There's only one vendor these days, starts with I and is in the UK. And you'll have to buy some acceleration from someone for the tensors, right? And you'll end up with an ugly architecture like that. And I call it ugly because you end up with 3 software stacks, right? One from each vendor. And then you have to do DMA copies because when you want to send data from yellow to blue, DMA, from blue to green, DMA, from green to yellow, DMA, more DMA is very difficult to program, lots of bugs, right? Latency, of course, if you're sending data back and forth, latency will be there. So there's nothing you can do there, right? And you're going to burn power. And notice those blocks in black that I call large cache, large SRAM. I don't have an opinion of what they should be, but I do know you'll have 3 of them. And your data, as it gets DMA from one to the other, will end up in at least 2 places, sometimes 3 places. So you're putting your data in 3 places, you're wasting area in your silicon, right? And unbalanced scaling. Okay, you launch your satellite, you're super happy. Now ESA wants the next satellite. How are you going to scale this thing? Well, you call the blue vendor and say, I need twice the blue performance. The blue vendor says, oh, sorry, we don't have that, or we don't have it on time for your launch. And then you call the yellow vendor, says, no, we're out of business. Sorry, we cannot ship you anything, right? So you're dealing with this triple supply chain that's not good. And I'm going to argue that it's not AI future proof. And I'll hold the thought and I'll explain later what I mean by that. Now, what is about merging? What is that we're doing different? Well, we're taking the blue, we're taking the yellow, and we're putting them all under control of the RISC-V CPU, the green guy, right? So everything you run on this thing is a RISC-V instruction. You want to run a tensor program or do a tensor matrix multiply, you write a RISC-V little subroutine, and we'll show that later, right? So you don't DMA or you don't program magic registers on your NOC saying when I write a 7 here, it's going to do a softmax. No, you write the code for softmax and you put it here, right? That's what we call all-in-one, right? And what do? You get a single software stack. So one, it's all RISC-V, one, right? You know DMA, I just said it, but I'll repeat it. You just have, you do loads and you do stores. All of you guys know how to do loads and stores. So there's no surprise in this architecture, right? Zero latency, literally those things are connected to each other at 0 clock distance. So you can move from one place to another at 0 clock distance, right? Notice there's now only one black box called optimized cache. The cache is just cache. I call it optimized because instead of having 3 copies as in the previous slide, you now have data only in one place, right? And it gives you balanced scaling. If you want to scale this thing, we'll see it in the coming slide, you just replicate it. So it's a very nice way to scale. And why I say it's AI future-proof, because now this thing is a CPU. It has an if and it has a while called branch, called a branch and a compare, right? With that, you can write any program. So I can say in confidence that whatever they invent 3 years from now, DeepSeek 11, I know it will run here. Maybe it doesn't run as fast as you want it, but it will run. So that is a key difference to all the other architectures on the market that are saying, no, buy my NPU separately and stuff like that, right? So let's go back to the picture. I moved it to the left. This all the ugly architecture with all the bad things. What does our thing look like? Well, you put multiple of these all-in-ones behind that cache and you connect it to the rest of the system. And so, if you need to scale, you just put more, right? That's how you program this. And all of you know how to program this. It's called parallel programming. All of you have done it, and all of you have one way or another run multiple threads on some architecture. So all of you know how to run this thing. There's no surprises here, right? And by the way, for marketing reasons, that's the picture I showed at the beginning. So if somebody's confused, that block is what we call the all-in-one, right? So let me mention a few features about the RISC-V part, about the Tensor unit. From a RISC-V point, we got a 4-wide out-of-order core. By the way, this morning we heard about a project from the EU. This one's better, I guarantee you. We got everything, user, supervisor, machine mode. We got hypervisor. It's Linux ready. So yes, this thing boots Linux. Of course, you don't have to. If you want to run in space with no Linux, I'm not forcing you, but you can. Right? MMU, SV39 and 48, for those of you that know what it is. Yes, we do have ECC on the D cache. Yes, we have parity on the I cache. Fast online, I mean, you read faster. I want to stop at CHI. CHI, if you don't know what it is the ARM protocol. Yes, I did say ARM. It's the AMBA protocol for coherent networks. So this thing is natively coherent. So if you want to build in space 8 cores that boot Linux in SMP mode, fully coherent, yes, this runs out of the box. So it is natively coherent. If you don't want to, we'll sell you the Axie4 version. So no religion here, you pick. It does have vector, as we said, RVV 1.0, vector crypto also is in there, bit manipulation, gazillion, which is our technology to be able to make many requests to memory and fully utilize the bandwidth of memory. And then we have a tensor unit. I'll talk a little bit more about that, but you have there the data types that you can see, that we support. This thing is highly configurable. So I gave you many more than this, but I put the big ones. Tensor unit, you can choose, the commercial names are T1, 2, 4, and 8. Basically, we use the int8 teraops per gigahertz. This thing can run from 500 megahertz to north of 2 gigahertz, right? So we give you the tops per gigahertz. So the T8 at 2 gigahertz would be 16 tops, right? So you have to multiply the numbers in the table times the gigahertz. And the vector unit is in gigaops, right? So it's different because we'll see later what do we use the vector unit for, right? Now, this is not useful if I just sell you the hardware without software. So we do have software stacks. There's more than one. And I'll talk about those two software stacks, like direct programming stack, which we call the Aliado SDK, and the AI software stack, right? The SDK, we have an IDE, of course. We have compilers, so GCC and LVM, emulators if you need them before you integrate this thing. And then we have AKL. Many of you might have heard about a thing from Intel called MKL, the Math Kernel Library, which contains lots and lots of algorithms already pre-optimized for you. That's what we're doing. We have the AKL, and we're going to give you a matrix multiply, matrix vector, FFT, you name it, right? And over time, we keep adding more. And if the one you want is not there, just tell us and we'll code it for you and ship it to you. And then this thing runs OpenMP and MPI. So, you have your usual set of tools. So if you want to program this thing as a normal CPU, we're more than happy to support you, right? And now is the time maybe that I talked about AKL to highlight this single software stack thing. And yesterday, Frank had the courage to put some instructions. So I said, I can put instructions too. And I wanted to show you that the very difficult matrix multiply in our machine is exactly 8 instructions. Lots of letters, but exactly 8 instructions, right? And basically, if you see on the right, that's the representation of a matrix multiply put in a cube. Don't be confused by the cube. Is the blue matrix A in blue A, the green matrix B, A times B plus the C produces a new C, right? That's what this code is doing. And you can see that basically this is just a loop. You should recognize it. VSET VLI is a RISC-V vector instruction you'll find in the manual. Add I is an instruction. This is the instruction, the one instruction that does matrix multiply. So from anyone programming this thing, yeah, you do have to read the manual. It's a lot of letters, but it is an instruction. So if you don't like our code or you can do better, we'll be more than happy that you can write this thing better than us. You don't need us if you can improve on that. And that's important for those of you that might be thinking of building a system that's going to be running many years, and you could be thinking, oh, what if these guys disappear? No problem. Everything is open. You recode it, you change the software, you upgrade the software. You don't need this in the middle with proprietary or secret interfaces. There's nothing secret in this machine. Okay, for AI, what did we do? For AI, we looked at all of them, PyTorch, TensorFlow Lite, and we kind of liked ONNX runtime. We thought it was the simplest, lightweight, easy to port, and really powerful, because all of the others export to ONNX. And Microsoft created this thing called ONNX runtime. Don't be confused. ONNX is a file format, and ONNX runtime is a program that reads ONNX files and puts them into execution, right? And so what Microsoft wrote is this blue thing where they read the ONNX model that you see on top, right there, right? So it reads the memory, the model, it parses, creates a graph, distributes, does lots of cool stuff. And then Microsoft, by the way, this is now open source in the Linux Software Foundation. So I say Microsoft because they created it, but it's now fully open source. Microsoft says, you want to target your hardware, you write an execution provider. And that's what we did. We added an execution provider using AKL, no surprise, drivers, and a few other things that target our hardware, right? That take the ONNX model and ship it to our vector, tensor unit, and cores and accelerate those things, right? And we have plenty of models already running, Llama 2, Llama 3, DeepSeek. Of course, we have to have DeepSeek, and I'll show another slide on DeepSeek. So it's really easy to get any model running. So if you are trying to deploy and your silicon wants to run some AI, well, you put our technology, you use our ONNX, and that's it. You download from Hugging Face your favorite model, and it will be running in no time. Yes, you may have to quantize, but that's not on us. That's on you. If you're not happy with the model, you may have to quantize it and things like that, right? So the second part of my talk, I want to show you how running transformers in this solution is. And I'll use Llama 2 FP16 7 billion, right? And just very quickly, this is Llama 2. This is the passes it goes through, and the key thing is what's called the transformer layer, which most of you already know. And the transformer layer is composed of an attention layer and a feed-forward layer, right? So if we dig down into the attention layer has all these passes, and the yellow ones are run on the tensor unit, while the blue ones are run on the vector unit. So it's obvious, or I hope it's obvious, that the fact of putting these things together is super useful, because you are running in the blue unit, the vector, and the data coming out of the blue unit immediately is taken by the tensor unit that's running the yellow stuff, right? So this is a really good thing to do. And this is the attention layer, and the forward layer is exactly the same. Yeah, here you have more vector than more tensor. So I think it should be obvious that you need to run these modern AI models, both the tensor unit and a vector unit, which I hope you already knew. But in case you didn't, you do need both things, right? You're not going to get away just with the tensor unit or just with the vector unit. And to prove you that, we run Llama 2, and we made this funny experiment just to run Llama 2 only on the core. So only the green part, nothing else, right? And we call that 1x speed. And we measured the different operations, right? So you got MATMOL 99%. So if you run it on the RISC-V core, 99% of your time will be on the matrix multiply. So what's your obvious next decision? Oh, I'm going to add a matrix multiply unit. Correct decision. And you run on the T1. What do you get? You run it on the one TOPS tensor unit, and you get this fantastic and amazing 170x speed up. That's pretty, that's a pretty big number, right? So of course, that's the job of the matrix multiply. You take that thing and it goes up, right? But very interestingly, for those of you that are in computer architecture and know Amdahl's law, something very interesting happened. Now we flipped. Now 80% of the time is spent on the blue guys that we were seeing before, not on the yellow guy, right? Now 80% is on that vector unit. So now is when you realize, oh, I cannot just have a tensor unit. I actually need to accelerate also the vector part, because otherwise I have an unbalanced plane flying like this in space, right? So what did we do? Then we run it on the tensor plus vector unit, and we get first an extra 3x speed up, right? Which is really nice, and that extra 3x is very welcome. But second, in my view, we get something as important, which is now it's a balanced thing. The 55-45, you'll call me, okay, it's not perfect. Yeah, it's very, very difficult to make it perfect, right? But it's now a balanced thing. So now we can think about, okay, this thing is good at running this piece, but I need more performance. No problem. We'll scale, right? And so you want more performance. You know, we have customers that buy one, we have customers that buy four, we have customers that are going bananas and putting lots, right? And I don't know what space needs, and I'm definitely not an expert. I would like to hear from you how much of this you need, but we got you covered, right? From just a little bit to a lot, right? So that's not a problem. And what I'm happy is that because these things are now balanced, the scaling is actually quite proportional, right? Can we run DeepSeek? Absolutely, we can run DeepSeek. I think we asked DeepSeek, what is 1 plus 1? And so this is our thing running DeepSeek and running 1 plus 1. Last summit I did with Llama, and everyone was, now it has to be DeepSeek, right? But the point about showing you and talking about DeepSeek is that, you know, a new model comes out. If you buy one of those hardwire architectures or architectures that are, you know, maybe specialized in softmax and matrix multiply, and DeepSeek comes and has another layer that you had not thought about, you are stuck with that RTL and you don't know how to run DeepSeek. That's never going to happen on our hardware, right? Now, maybe we don't run DeepSeek perfectly at 100% performance. I admit it. But we guarantee you will be able to run it. Right? And yes, maybe you will run it a little bit below, but you're going to be fine. So even if you've launched your satellite, it's in space, and you find a new algorithm that's better with our technology, you could upload the new software and run it. You're not bound to exactly one type of model, one type of architecture, one type of solution. So we do have the best IP, out of order core, out of order vector unit. The core, I'll use the time to talk about Gazillion for a second. The core is out of order, so it is you know, reorganizing vector loads, vector stores, scalar loads, scalar stores with the tensor multiply, the vector adds, vector multiplies, and the scalar integers and the branches. So the core is taking care of everything, right? I didn't talk about the Gazillion a lot, and it's actually really important. What is that thing doing, right? What is that thing? Well, when you have a tensor unit that wants so much data, right, somebody has to guarantee that the data will arrive from memory or from SRAM or from whatever into the tensor unit, right? And if you do that with a normal core that's not from us, what happens is that you start loading data, you look into the cache, you have a cache miss, and you stop. And you wait 100 clocks, and then data comes back. And then you give it to a tensor unit, the tensor unit goes, zoop, consumes it in no time, right? Then you get the next bit of data, you wait another 100 clocks. You give it to the tensor unit, and the tensor unit consumes it. Well, you have the tensor unit running at 1 divided by 100 of its capability. This makes no sense, right? So that's why we added this thing called the Gazillion unit, which is, its job is to, you make a load, it goes out and gets it. You make another load, it goes out and gets it. And we never stop. In fact, we support up to 128 requests to the memory system, right? So one of these things can consume between 64 gigabytes per second at 1 gigahertz, 128 gigabytes a second at 2 gigahertz, and more if you go to AXI, right? So some people get scared when they hear these numbers. They say, oh my God, we don't want to put this in our system because we don't even have 100 megabytes of memory bandwidth, right? You know, if you're running AI, you need bandwidth, and that bandwidth has to come from somewhere, either a local SRAM, which we can put, or memory, or both, right? But you want a core capable of taking that data and using it. And if you're wondering, well, I'm not following him, why do I need to bring so much data? Look at the size of Llama 2. It's 14 gigabytes. You're not going to tell me you can have a 14 gigabyte cache, right? Because I'm not going to believe you, right? So because you're not going to have a 14 gigabyte cache, the data has to come from somewhere. And somewhere is called memory, right? So you need a core that's really good at bringing memory. So the core with the SDK, if you don't like our ONNX or you whatever, you can program this thing your own. Or if you just want this thing to run AI, you don't have to be bothered with anything. You install ONNX on the host machine, and you run it there. And I forgot about space, but okay, what do we have about space? Well, we do have ECC, we have parity. I forgot because I was doing this just before lunch about RARI. Somebody was speaking about RARI. We do have all that interface stuff to report errors. And rad-hard, no, well, we've never done it, but that's why I'm here. Looking forward that someone will come the coffee break and tell me, oh, we want your technology, we want to put it in space. How can we do it? So with that, thank you very much for your attention.